Hello everyone, welcome to your second physics tutorial. So recall from the previous tutorial we just talked about motion and how motion can happen in 3 dimensions. Right now we're going to focus on motion that only happens in 1 dimension. One-dimensional motion is very easy, but you can extend it to 2 and 3 quite easily. So we're going to study one-dimensional motion in pretty deep detail, and then we're just going to quickly glimpse over 2-dimensional motion, and 3-dimensional motion we won't even touch because it's a really easy intuitive extension from 2-dimensional motion. So once again, when we're describing motion, what are the parameters or what are the properties of motion that we're interested in? So the first thing that comes to mind when you're describing motion is you're interested in basically its position. Where is it at? So let's list some properties of motion that we are interested in. The first thing that we're interested in is its position. Now remember, all of these properties are going to be relative to some frame of reference. And remember, we picked our frame of reference as the origin of the axis, and we get to pick wherever we want to place that axis. And I know right now it's a little bit abstract, but I'll give a concrete example. Just try to keep these things in the back of your mind. So we're always interested in knowing where something is. We're also interested in its velocity, or in other words, we're interested in knowing how fast it's traveling. A third property that we're usually interested in is acceleration. Acceleration is just, you may have some intuitive understanding about this, it's at the rate at which your velocity is changing. So how fast your speed is changing is called your acceleration. These are the 3 properties of motion that we are very interested in. We usually want to find these things out. We're often given a few of these and we're asked to find the other one. And I'll show you guys how to do that. Now let's go ahead and talk about each one of these a little bit more, maybe create a few drawings so that we really hammer in and get a really good picture of what they mean. So let's go ahead and talk about position right now. Now I guess I'll go ahead and use my flagpole example again. So I'm going to put a little flagpole here. I guess this is a flagpole. And then I'm going to put a person right over here. So now, if I'm going to be describing my position relative to the flagpole, that means I have to choose my frame of reference as the flagpole. So I'm going to choose my frame of reference. Now I'm going to go ahead and make that red. So here's my frame of reference. Now that means that when any properties of motion that I describe will be relative to here. And then I also need to choose direction. So I have to choose my dimensions, and usually you pick the x as the left and right, so this is going to be x, and then this is going to be y, which is forward or backward, and then z is going to be up or down, but we usually don't even touch it, so just worry about x and y. Okay, so I have my frame of reference, or in other words I have my coordinate axes, and now when I describe this guy's position, I'm describing it relative to here. So relative to here, where is he at? Now let's go ahead and talk about and visualize what velocity is. I'll go ahead and do that right over here. So we'll use the same exact example. Okay, so we have this guy again, and he's moving relative to the flagpole again because we put our frame of reference right here and we chose that as our y dimension and this is our x dimension. So let's say that he moves from here to over here in some time, and we're just going to call this time delta t. So in some time delta t, this could be 1 second, 2 seconds, 3 seconds, I'm just being general. In some time delta t, he moves some distance, and we're going to call that delta x. Now again, this could be 1 meter, 2 meter, 3 meter, whatever, but I'm just being general right now. So in some time delta t, he moves some distance delta x, and the ratio of this delta x to delta t is defined as velocity. So now that's very mathematical. Let's describe velocity intuitively. Velocity intuitively just tells you basically how fast he's moving. Now, velocity also tells you the direction that he's moving in, because it's a vector. So maybe this is a good time to take a little detour from the physics and learn a little bit about the math. So sometimes, besides numbers just having basically a number, they also have a direction. And velocity is one of those cases, because velocity tells you the speed that he's traveling, so how fast is he going, and also what direction is he going in. And that's what makes it a vector. So a vector has what's called a magnitude, which in this case is how fast it's going, and it has a direction, so which way it's pointing. And clearly this guy is moving from here to here. So our velocity vector would be something like this. That's our velocity vector. And you represent vectors by putting a little arrow above it. It could be a half arrow or a full arrow. So don't worry too much about learning exactly what a vector is or the things that we can do to a vector, but just know the following. Sometimes in the real world, there are quantities where just the magnitude or just how big or how small it is doesn't matter, but it also matters which direction it's pointing at. One obvious thing is velocity. When somebody is going at some speed, sure, it's important how fast they're going, but oftentimes you're also interested in which direction he's going in. And to solve this problem, basically you use vectors. Maybe that's why vectors were actually created, because there's so much, it's so often that in nature and in the real world, we are interested in both how strong a certain number is and which direction that it's pointing at. So that's all you should know about that. But to get an intuitive feeling about what velocity is, just think about how fast you're going and in what direction you're going at. Now let's go ahead and quickly similarly talk about acceleration. And basically acceleration is going to be how fast your velocity is changing. So just like how velocity is how fast your position is changing, acceleration is how fast your velocity is changing. So to summarize, I guess, basically, let's make a little table here. A table of property. So this is going to be the property of motion. Okay, so we have three properties. And then we're going to talk about an intuitive definition. And then we'll also list out the mathematical definition. So the first property that we talked about is position, and we usually represent, so I'll write position, we usually represent position as an x. And the intuitive definition of position is where you are at relative to your frame of reference. Or in short, just where you're at. And mathematically, there's not much to say. It's just going to be the value of x, I guess. And then velocity, we usually represent it with the letter v. And it is important to remember that it's a vector, but please, I guess right now you shouldn't really worry too much about vectors. We're going to talk a lot more about vectors when we get to two-dimensional motion. So just, I'm sorry to say this and I don't like doing this, but just kind of don't worry too much about what a vector means. Just kind of have an intuitive sense as to what they are. So an intuitive definition of velocity is how fast you are going. Okay, how fast you are going. Or another way to put it is how fast or how much your position is changing. How fast your position is changing. How fast your position is changing. So the faster that your position is changing, then the greater your velocity. And then let's talk about a mathematical definition of velocity. So we said that velocity is how fast your position is changing. So let's take the magnitude of the change in your position. So how much of your position changed, we'll call that delta x, just like we did up there, and how long it took for that change, that's delta t. And you can kind of think how this intuitively gives you how fast your position is changing. Because if I change this much distance in this little time, then clearly my velocity is very big, you know? So the ratio of how much your position changes, this is how much your position changes, to how long it takes to make that change. So the more that your position changes and the less time it takes to make that change, then the greater your velocity. And that links nicely with its intuitive definition of how fast your position is changing. Similarly, for acceleration, just an extension, we usually represent it with the letter A. And an intuitive definition of acceleration is how fast your velocity is changing. So similarly, mathematically, we define it as, okay, so if we want to know how fast your velocity is changing, well, let's see how much the velocity changes, and we call that delta V, how much it changes, and how long it takes for the velocity to change that much, and we call that delta T. Okay, so now just a quick little mathematical side note is that basically whenever you see this delta sign, so whenever you have, so we'll just do math note, I guess, right over here. So whenever you have delta something, that just means the change in that thing. So it's going to be equal to that something final minus something, that same something initial. So if I tell you the change in my money, I guess, is going to be my money final minus my money initial. So if I finally had $20 and initially I had $10, then the change in my money is 20 minus 10 or 10. Let me see if that makes sense. It's going to be final minus initial. So if I had 20 finally and initially I had 10, that means, yeah, I gained $10. So that makes sense. Let's get rid of this example. Don't read it in our notes. So just kind of remember this. Whenever it's delta something, it's that something final minus initial. The order of this is really important. It's always final minus initial. So why are these relationships important? Well, this is because these they describe motion, and oftentimes we know some things about motion, and there are things that we don't know that we wish to know. So that's why it's important that we know these relationships, so that if we know 2 out of the 3, we can figure out the third. So for example, so we'll do some quick problems. So if I tell you that I'm going 3 meters per second for 5 seconds, okay, so if I'm going 3 meters per second for 5 seconds, how far have I gone? Now this is a really simple question, and your intuition just tells you if I'm going 3 meters per second for 5 seconds, I just do 3 times 5, and my intuition tells me 15 seconds. Well, you can also do this mathematically, so let's do it mathematically. This 3 meters per second is telling you your speed, or your velocity, and we know that velocity is equal to delta x over delta t. So velocity is equal to delta x over delta t. Let's just quickly check, and this makes intuitive sense. How fast you're going, it's going to equal to how much distance you cover and how much time you take, over how much time you take to cover that distance. That makes sense. So anyways, now we know our velocity. So we know this. And then we also know the time, the delta time. So now we can find out how far we have covered by solving for delta x, since we know this relationship. Now we just solve this equation for delta x, and I'm going to assume that you know how to solve equations. So I multiply both sides by delta t. I get delta t v is equal to delta x. So how far I travel is going to be my delta t, which is 5 seconds, times v, which is 3. So I still get, mathematically, I still get 15 seconds. And there are different situations. In some situations, you're given different variables and you're asked to find for a different one. So it's easier for me to explain through examples. What if I told you something different? For example, what if I told you I covered this should not be seconds. My units are wrong here. If I'm going 3 meters per second for 5 seconds, how far did I go? I went 15 meters. What if I told you that I covered 15 meters in 5 seconds, okay? I covered 15 meters in 5 seconds. How fast was I going? Again, your intuition can kind of tell you that, okay, I simply do 15 meters in 5 seconds and I get 3 meters per second. That's what probably your intuition tells you. But you can also do this mathematically, because you know that velocity is equal to delta x over delta t, and in this case I gave you how far you went, so I gave you this, and then how much time it took you to go that far, so I gave you this, and then I want you to find out how fast you would go. So all you do is plug and play. So you plug 15 here, and you plug 5 here, and you end up getting 3 meters per second. So basically, as you can see, the reason why we need to know these relationships is because oftentimes these parameters, the position, the velocity, and then sometimes even time, we want to know. We want to know these things for certain motion because they're useful to us. Describing maybe the movement of a plane or the movement of a train, how long it's going to take you to get to work if you know the distance, etc. So these are parameters of motion that we're interested in. So if we know some relationship between these parameters, then we can find out some things that maybe we can't really measure or we don't want to measure. Like, what if you don't want to measure the distance from your home to your workplace? If you don't want to carry a ginormous measuring tape from your home to your work, you know, that's stupid. You don't want to measure it that way. So you can easily measure it by timing how long it takes you to get to work and how fast you are traveling. So they're very useful in those situations where you can't measure a certain parameter of motion directly, but you can figure it out because you know the relationship between those parameters. So it's really important that you know the relationship between velocity, position, and time, and then you know the relationship between acceleration and the change in velocity and time. I was supposed to be change in position. So that's why these equations are important to know. And it's important to kind of understand them. They're not just like an equation with little variables. This is telling you basically the change in how much distance you cover and how long you cover it, and we call that your speed. And this tells you basically how fast your speed is changing and how long it takes for that change, and we call that acceleration. So they have meaning. Anyways, I think this pretty much covers the basics of position, velocity, and acceleration in one dimension. We're going to expand on this a little bit more because what I've talked about so far is the average velocity and the average acceleration. So I should really put a little average sign over these. That little bar above the variable means average. So average velocity, average acceleration. That's what I'm talking about. So for example, when I said that you're going 3 meters per second to work, on average you're going 3 meters per second to work. But you could be at one point going 0 meters per second. For example, when you stop at a stoplight, you're going to go 0 meters per second for a little bit of time. So at different instances in time, you're going at a different speed. And we call that your instantaneous velocity or your instantaneous acceleration. And we're going to cover those in the next tutorial. Thank you for watching, and I'll see you guys in the next tutorial.